Right. Recording. Good. Okay, next lesson. Electric field strength formulas. Or really, I should perhaps say formulae. Oh well. Yeah. Continue. Okay. Different charges will produce different electric fields. Makes sense. And we're going to have a look at 4 types actually. That is point, sphere, parallel, and dipole. So anyway, these are different, okay, not different types, because electric fields and electric fields, different patterns. Let me explain. So the first one is what's called a point charge. So if you just have a charge by itself like a negative, the field looks like it's going into the charge. Now of course this makes sense, because if I put a positive charge here, what will happen? It'll move in. And for the positive point charge, the electric field looks like it's moving out. And again, this makes sense, because if I put a positive charge here, it will be pushed away. Now, before continuing, I should say it's a fairly common exam question to ask you to draw one of these fields, and there's 4 to learn. So the first one is the point charge, which is these 2 possibilities. So please draw these 2.
They are point charge.
Yeah, point charge, electric field.
This is point charge 2. This is point 2.
That's actually 2 pictures. Yeah, 2 different pictures.
But they should be together.
No, you can have them by themselves. These are 2 pictures now. Yeah. Okay, next one. Next one is if you have a sphere. And the point here is it's the same. If you have lots of positive charges together, then it's the same picture as just one positive charge. Do you see? That's the point, that a spherical charge, it just looks the same as a point charge. The only difference, literally the only difference, is a spherical charge is just lots of point charges put together.
Negative.
No, all of the same type.
Here.
Well, in this picture, all positive, yeah.
So we draw it the same way as we drew the point charge.
Basically, yeah.
We should draw it spherically.
Yes. Beautiful. Work of art.
Yeah.
Okay. Next one. Next one is one you haven't seen, the parallel plates. So you can get an electric field between 2 plates. If this is a positive plate and this is a negative plate, then you have a field that goes straight down. Curves a little at the end, but basically goes straight down. So electric field strength.
Why they curve? I don't know.
complicated, but you never get anything perfectly neat. Whenever you have a boundary, you know, like a wall, there's always sort of a spilling over, you know. In real life, nothing is nice and neat. There's always going to be sort of a spillover. The field is leaking out.
Leaking?
Like water leaks out nearly. There's parallel plates. Yeah? Yeah? Continue? And the fourth type is one you've seen already. The fourth one is called a dipole, and this is when you have a positive with a negative, like this. Okay. Continue?
Yeah.
Yeah. Now, in addition to the electric fields, we also have something called potential lines. Let me try and draw. Oh, I'm sick. I'm working too hard and it's making me sick. Right. Here's an example. Okay, here is the ground. Here is a person. And of course you all know that there's a force downwards here. So if you imagine it's like there's a vector field like this. And if he has this little ball and he puts the ball here, it'll fall down, here it'll fall down. So this is like the field, so to speak. But you also know that there's a potential energy here, and that's equal to mgh. So if he puts the ball anywhere here, it'll have the same potential energy. Why is the potential energy here and here and here and here all the same? Same height. Now this line here, this is different to this, right?
Yeah.
But everywhere on the line is the same. These are called equipotential lines. The part of the space where the potential energy is the same. And now I'm going to draw these lines. Yeah. Yes, I can draw them now? Yeah? Okay. So the first one, the point in the sphere, let me draw an example. So let's say I have positive here, and there's a field going out. What what do you think the equipotential lines might look like? Yeah, should just be circles. Like this. So what I want you to do is to add to your picture the equipotential lines, which look like this. Now, yeah, just to your picture, the two pictures, yeah. The next one, because you have a point and a sphere. It's the same. It's just circles around it.
But not the dipole.
No, we'll have to get to the dipole and the plates. So what do you think about the plates, where you have a positive and you have a negative plate and you have a field going like this? What do you think the equipotential lines look like here? Yeah. I think they should just be horizontal lines. But the last one, oh, yeah, I hate this one. It's like this, isn't it? Did I draw this right? I know it's ugly. Ugh. Alright. So here it's a circle we expect, okay? And a circle. And here it's a circle and a circle. Yeah? But what about here? Should I don't know what I'm doing. No, it doesn't make sense. I don't like it. Yeah, should it still be circles? Look, that's what Google's for. Let's find a wonderful picture. It will be circles here and here. I'm just not sure what happens when they come together. Because my thinking is, Google will tell me what to think. Huh? No, I'll get it. I'm not sure if they connect or if they stay as circles. Oh, come on.
Like this.
You're thinking like this?
Yeah.
I don't know.
Like
Oh, could someone type it in on their phone? You have it? Well, describe it to me. Wait, come back, come back!
green line.
Yeah. Right, it's like this. It is circles, still, but in between it goes like this. You have these sort of vertical lines. This with this? No, they're separate. I'm trying to find a picture that's better to show you, but it's just not loading. Anyways, if you wanted a wonderful picture, you can just put into Google Images equipotential lines for a dipole. They might be extremely large circles. Do you know what I mean? Like, they look roughly vertical, but you're saying that if I was to zoom out, I think you might be right. Yeah, they're not concentric perfectly. You're saying that what you mean is that it's like this. Yeah, I agree with you.
Potential energy is the same.
But for the exam, what I care about seeing is circles, circles, and these vertical lines. Yeah? What?
The potential energy on the circle of positive.
Yeah. It's different to negative.
Different?
Yeah. Oh yeah, because these are separate lines, because they don't touch. So everywhere here the energy is the same, and everywhere here the energy is the same, but these might not be the same, because they're different lines. Okay, continue. So, next. The parallel plates. Let me just close this. It's never loaded. So we have our two plates, and this would be positive and this would be negative. Positive, negative, and by the way, this is usually a vacuum in between the plates. How do we make this field? In fact, this is a very easy field to make. I haven't shown you how to do that yet. The way you do this is you take a cell and you connect the positive to a copper plate and the negative to a copper plate, and then that's it. It will make an electric field here. But how strong is the field? It will depend on two things. It'll depend on the distance between the plates, and also, what else do you think it might depend on?
Voltage.
Yeah, what about it?
The potential difference.
Yeah, the voltage of it. Yeah. So what do we expect to happen to the electric field here? Should it be bigger or smaller if the V is bigger?
Oh, bigger.
Makes sense, doesn't it? And the D. I want to make this bigger. What should I do to the D? Smaller. So it is not a surprise that the formula would be this. That if you have a current passing through two plates, and they're a distance d apart, and the voltage is V, then you get an electric field, and the strength is given by the formula V over D. Okay, so you'll need to note this, please. No, I'm just giving you the formula. You can write or draw a picture. I'd say you are thinking about drawing a picture. Am I right? Oh, sorry, hang on. You're thinking of not a picture or writing and just putting the formula down. Am I right now?
No.
And then what?
I write it down.
What? Are you feeling okay? Oh, it's strange.
If I have plate,
Yeah,
this is plus, this is minus,
yeah,
this is voltage,
yeah.
I put my finger here.
You'll be okay.
Will be okay? No fear, cold or hot, something like
No, it depends. How big of a voltage?
If this is so bigger, so big.
What voltage? How big?
100.
100 volts?
No, 1 million.
Oh no, don't do that.
It's okay. Nothing happens. This.
You can try.
Yeah, try.
I know.
No, I wouldn't say nothing would happen, because I mean, think about this, okay? Your skin is made of atoms, which have protons and electrons. Maybe when you put your hand in the electric field, the protons will get pulled up, or pulled down to the negative plate, and the electrons will get pulled off the protons and ionize. So you might just ionize your hand, strip the electrons off your hand, and I I could imagine if it was strong enough it could damage you.
We can see this. What happened in this place?
But you can see what happens. Oh yeah, well.
We can see the electric field.
We could see the electric field. What they usually do, you could have some kind of, maybe put in some kind of gas, a gas that has a positive charge. Then you could see the gas move into the negative plate. Do something like that. Okay, do we have this? Yeah? Continue? Yeah? Bruce? Yeah. Okay, now, we have a different situation if you have a point charge. So imagine I have a positive charge here, and there's a field. There's a field. And I want to know what's the electric field strength here, for example. What do you think that would depend on? What do you think would affect how strong the field is here? If we think, yeah, we feel like the distance should affect it, shouldn't it? Bigger distance would have what effect?
More.
Yeah, so it should be down here somewhere, the distance. Anything else here that might affect it? Well,
Charge.
how much charge we have. So again, maybe it won't surprise you that when we have a charge Q, the electric field strength is this formula. Now let me just explain. The R is the distance, the Q is the charge, and this thing here is just a constant. It's just a constant. Its value is this, which is on the calculator. So this guy here, that is just a constant. In fact, a lot of the times it's just written like this, as just a K. Now I don't, that's fine. The problem is this is in your formula book, but it's not on the calculator. Whereas this one here, or rather I should say this part of it, that is in the formula book and is on your calculator. So if you just want to type it into your calculator, it might be better to write the constant in this form, because you have this constant on the calculator.
What's jumping to?
Oh, this is epsilon 0. So if you can write the formula down. Epsilon 0.
Times the Q over R
Squared, yeah. Let's work out the units for epsilon. Okay, so if E equals 1 over 4 pi epsilon 0 Q over R squared, then epsilon 0 is 1 over 4 pi E Q over R squared. So if I want to know the units, it'll be the units here. So on the top I have coulombs, on the bottom I have newtons per coulomb, and this one here is meters squared. So I can take this up to the top, and it's coulomb squared per newton meter squared. So that would be the units for epsilon 0. By the way, if you're using K, the units for K would be reversed, reciprocal, because remember the K is like this. So the units for the K would be newton meter squared per coulomb squared, because it's upside down. I think it's worth noting that. Continue. We continue
Go back.
to this. You really want to write the whole thing down?
No.
Calvin, what constant number is epsilon 0 on the calculator? 32? Thank you. Continue. So, let's have a look at an example. Two horizontal plates have a voltage of 200 volts between them. The positive plate is a centimeter above the negative plate. Okay. So you have two plates, positive, negative, and it's 200 volts between them. And the distance is also 1 centimeter between them. And you have half a milligram of charge 10 to the 10 E falls from the top to the lower. So there's a charge here. That's kind of a no, it is positive, sorry. That's 10 to the 10 E, the charge here. So that's a lot of positive charge. And this will be pushed away from the positive and pulled towards the negative. So it should actually move pretty fast, I would think. Pretty fast. So the time should be, I think, pretty small. And you know the mass of it is half a milligram. And my question is, I want the time to fall. Okay. Can you calculate that? Or is that a little too hard? No, I think that might be a little bit too hard. We'll do it together. So, what type of problem is this? It's actually a UVATS. The U, we know. What is it? 0. The V? We don't know. The A? We could know. The T is what we want, and the S we do know. The S is minus 0.01. Right, how can I get the A, Wookie, since you said we could know it? Yeah? Oh, because it's going down. I'm just taking down as negative. Yeah, we could say the A is F over M. Right, well, do we know the M? We do. It's 0.5 times 10 to the minus 6. Do we know the F?
We could know.
We could know it using what formula?
E equals V over.
Yeah, EQ. Yeah, that's it there. The E times the Q. Is that the F?
No.
There's another force.
That's the weight.
Yeah. The mg. Okay, so now actually, do we know the m? Yeah. Do we know the g? Yeah, and we know the m again. So I'm not sorry. Let me just put it as m. EQ plus mg. Okay. So we're good. We're good. We're good. We're good. But do we know the electric field strength?
Yeah.
Yeah. Well, we could know it. What is it?
V over D.
The new formula, V over D. Now we're good. Alright, so it seems like it's just, we have to put everything in the calculator. So, here is, what did I say, 0.5 times 10 to the power of minus 6, yeah? And then 0.5 times 10 to the minus 6 times 9.81. But in front of that I should have another fraction. No! Sorry, that was a bit dramatic. Let me just start over. Fraction plus. Okay. 0.5 times 10 to the minus 6. V is 200. D is 0.01. Q is 10 to the 10 E. And then this is M. G. Alright, it's a bit of a pain, but when you type all the numbers in, you get an acceleration of syntax error. You get an acceleration of 73.9 meters per second squared. Extremely fast, isn't it? Alright, so what formula will give me the t here? Using UVATS, what one would be best? S equals ut, which is 0, and then a half at squared. So the t will be 0.02 square root over a, which is actually technically a minus since it's going down. Okay. Not 0.0165 0.0165 of a second. So fires down. Messy, but not too hard. Yes. Next example, yeah. 2s. Yeah.
Why is there minus?
Oh, the minus again. I like it because down is minus and up is positive. So technically, Shamsa, that should be a minus there because it's down.
Thank you.
I don't know if you're really happy with that. You don't like this, no?
Not really.
Yeah, okay. Right, next example?
Yep.
Alright. I think this one you could do. You have an electron that's 2 millimeters away from 3 protons. What is the force?
Force.
So we have to use the second formula. Now give that a try. Yeah.
Why charge?
Yeah, the epsilon one. Huh?
B.
No, you're using the plate formula. You need to be using the second one.
The 1 over something?
Yeah. So Shamsa, how was that burrito?
That's good.
Too much food for you?
Yeah, that sounds good.
It was good.
Cheaper.
How much was the burrito?
Wouldn't it was 61?
So I'm thinking about my lunch now. What to get? You would recommend it?
Yeah, nice.
Spicy?
Yeah, good spicy.
Good spicy, okay. Maybe I'll try the burrito then.
What does it mean, good spicy?
Good spicy?
Spicy?
Not too spicy.
A little bit spicy?
Yeah.
No, I got too spicy.
Oh, okay. She likes spicy food.
How
Yeah.
much spice?
I don't know. Got an answer?
No.
Got an answer, Bruce? No? Okay.
1 minute.
Okay.
30 seconds.
30 seconds, fine. I'll give you 30 seconds.
Bum, bum.
Anyway, Shamsa, my favourite is still the chicken, hang on, let me think, shawarma. It's still the best. Have you tried it?
I know.
Okay,
Yeah,
are you?
it's the best.
It's the best. Got an answer, Wade? Audrey?
1.15 times 10 to the 12 negative 22.
And how sure are you? Are you 100% sure?
No.
Okay, good. You shouldn't be 100%. Let's calculate it. So, the formula is 1 over 4 pi epsilon 0 squared, yeah? Times, now,
Y square.
yeah, y squared, Stephen. I was thinking of the next part of the formula with the or. Now, on the top, is it 1 electron charge or 3 protons of charge?
3.
Very good.
You think on the question.
Explain to her why, Bruce.
The question.
That's true. But why not the electron? Why the protons? Well, because it's the protons that are the cause of the electric field. Okay. And then here, what do I have on the bottom?
R square.
R squared, which is 2 times 10 to the power minus 2 millimeters. Were you right or wrong?
Is it wrong?
I'm wrong.
Yeah. You need another electric charge of electric.
Oh, this is just the electric field strength. I'm not finished yet. I'm being too impatient. Yeah, so the F equals QE. I've just worked out the Q.
You work
The
out.
Q is
Hang on, shh. The problem is I'm still thinking about should I get a burrito or chicken, and this is the problem. E equals F over Q, so F equals EQ. Okay, and I've just worked out the E, and now I need to multiply by the Q. And the question is which Q, the electron or the proton? Electron. Yes. Why? Okay, because in this formula here, the Q is the Q that's in the field. What you need to picture here is you have 3 protons and they're making a field. And you have an electron which is in the field. So the formula E equals F over Q, that Q is referring to the electron that's in the field. And the formula E equals 1 over 4 pi epsilon 0 Q over R squared, that Q is referring to what's making the field. Yeah.
What's the E for that one? The E is everything around.
Which E? This E?
Yeah.
That's the electric field strength at a distance of 2 millimeters. Yeah. So I get 1.73 times 10 to the minus 24 newtons is the force.
I've got
What?
10 to the minus
Give me.
22.
You got 10 to the what? 22. Is that not, what did I get?
I guess the same.
Which? 2 or 4?
1.7.
10 to the 24?
Yeah, 24.
Oh, bad teacher. Bad teacher. I've made a mistake on my calculator. What number is wrong? And it seems like you made the same mistake if you got the answer as me. Bad teacher. Bad teacher. Millimeter.
Yeah.
Minus 3. 22. Thank you, Wookie.
What was the answer for E?
Oh, it's long gone now on my screen. I can try and go back and get it. Oh, I can get it here in a second. This is just the final answer. We'll just write that down. Apologies, 22. Okay. Sorry, you wanted the answer for the electric field strength. So I'll just delete this here. That's what it was for the electric field strength. Oh, so that means... Oh, okay. Because I had 2 in there as well, didn't I? In the denominator here. Yeah, so this is the correct electric field strength now. Yeah, it's okay. Fine, fine.
What is the E for that one again? The red E. I know in my paint.
This one?
Yeah.
Electric field strength. Effectively, you've got 2 formulas for electric field strength. This here gives me E, and this also gives me E. So it is correct to say F over Q is 1 over 4 pi epsilon 0 Q over R squared. Now, to be clear, this is the Q for the electron, and this is the one for the protons.
How do you know that's for the proton? The Q for the proton?
Here, because this is the formula for the electric field caused by a charge Q, and this is causing the field. Whereas this is a formula for the electric field strength if you know what force is being exerted on a charge Q. So it's almost like this one is the cause of the field and this one responds to the field. Yeah. Is okay? Can never tell with Audrey if it's okay. She has a very good poker face. I can't tell. She's a good poker face? Yeah. You know poker face? Yeah, I can't tell sometimes if you're saying, yes, I understand this, or he's crazy, I don't know what he's saying. I can't tell the difference. Yeah. So I'll have to trust you if you say it's okay. Alright. So, next now. Only 3 questions.
Not only 3.
Yeah, only 3. So,
How could you do that?
yeah, 1, 2, 3.
A, B, C, D.
Oh, that's only part of a question. Yeah. I think you might need to take a picture of this on your phone because there won't be time to do it now, so you'll have to do this one at home. Well, we have 2 hours tomorrow?
1 hour.
Just the 1 hour?
Yes.
So I want to use this 1 hour for assessment support. I want to see what you've done on Excel, and then I want to continue with that. Try this for the weekend, and then next week we'll have a tutorial on these 2 lessons.
When?
I'll say the first class next week.
You do every question?
I'll do every question
With the record?
and record. I think you would like this.
I'm hungry.
Okay, burrito time.
Yesterday?
Close this.
Yeah.